Okay, let's get started. So welcome to the second workshop. I think some of us were at the first workshop, which was back in 2019 or so. So we're going to be talking about sparse tensor algebra today, and the workshop will be pretty rapid fire, like the first workshop, with 15-minute talks. So I'll be timing them. I'll give like the 5 minutes, the 3 minutes, and so forth from the side here. After each set of two or three or four talks, we have a 10-minute, 15-minute discussion. So then the speakers can just gather here, and we'll have a little bit of a questions panel, just general discussion. And then at the end, we're going to have a poster session outside. So we have 11 or 12 papers, only from 3 institutions, but I think it'll be fun. It's more for everyone to just be able to hang out and discuss than it is for sort of people pinned to their posters kind of poster session. So let's just get started. So I'll get us started with my talk, and then it's going to be Mary, and then it's Goxen. What I won't be talking about is just a quick sense of what I think is important for sparse for software and hardware for sparse machine learning. So we've seen a lot of dense machine learning coming up in all the companies, foundation models and all of this stuff. But mostly they reduce their operations to dense tensor algebra, and mostly they reduce it specifically to dense matrix multiplications, although some of them fuse them. And then they can target TPUs and such. And this reduction to dense matrix multiplications and then targeting a TPU, going to be talking about why I think that's maybe not the best idea for sparse tensor algebra. So a little bit of an overview. I'm going to be talking about basically why sparsity requires compilers and more general hardware than just a matrix multiplication unit. And then the thesis is that unlike dense neural networks that can be reduced to a gem call, whether implemented in hardware or software, it will not be possible to reduce sparse neural networks to one optimized function. Okay, so first a little bit of my view of sparsity, or our view of sparsity, I'm sure. So if you have a matrix like this, and I've colored in the non-zeros, and the zeros are white boxes, then the way to think about it is not as an n by m matrix, but as a connection between sets of concepts. And those concepts can be people, or it can be anything else. And that induces a graph of the sparsity connections of this matrix. So this is the system that the matrix models. So a matrix model is a linear relationship between concepts in a system. Thinking about it that way, we see really 2 or 3 types of sparsity in the neural networks. One is learned and one is a priori, meaning it's there whether you use it or not. So for instance, if you start out with a bunch of concepts and you know nothing about those concepts other than certain quantities on the different concepts, so maybe these are people and you know something about their ages and so forth. And if you know nothing about the relationships between them, then you just have to hypothesize that it's a dense connection, so everything is related to everything and everything influences everything. And that's why you get a dense weight matrix. And this is really a fully connected system. And you can, of course, try to prune that matrix and get maybe take the smallest values and cap them down to 0 to make it sparse. But there's a limit to how much you can do that in practice. Maybe we can push that limit and we can make it extremely sparse, maybe 90%, maybe 95%. But it's hard to make it really, really sparse, so sparse that it's obvious that you need sparse techniques. It can maybe be done, but it's difficult to really push that envelope. But then you have another set of sparsity where the sparsity comes from the system you're modeling. So instead of having some set of concepts with no relationships, maybe you have a graph of concepts where you already know something about friendship relationships or employer-employee relationships or anything like that. And if you have that, you already have the sparsity in the input. And if you have sparsity in the input, you can take advantage of it. So for instance, when we're using convolutional neural networks, we know that pixels next to each other may have some relationship with respect to the thing we're trying to model. If you care about edges, then adjacencies in an image is important. And if you care about social structures, then social relationships are important. So if you have such an a priori structure, then we can use something like a graph neural network. And it's not really about that model design, it's about the input. The input being a graph and being very, very sparse. So this view really just tells us that whether there's sparsity enough or not in the neural network has a lot to do with what kind of data you're learning something about or inferring something about. So if you have just a set of objects, you may have just a set of objects where you don't know anything about the relationships. So you have to postulate a fully connected layer because you don't know what's connected to what. And then maybe you can start to learn by pruning what's connected to what. But now you need a lot of input data and a lot of computation to learn those connections. Or you may have a sequence, like in the language models, and then maybe you can take advantage of that sequence structure, that words follow other words, to improve the computation a little bit. Maybe you have a transformer with a triangular matrix, so you cut out some computation going, so you're not looking forward. The words are only connected to words coming before, for instance. So that helps regularize those networks, but it can also be used to increase the performance by up to 2x because you're cutting out half of the work. Or if you have recurrences in recurrent neural networks, then they go forward as well, although we don't use them anymore. And then you might have a grid structure like the pixel locality in CNNs, and then you want to take advantage of that with something like a convolutional neural network. And then we've been seeing recently a lot of interest in sparse attention mechanisms in transformers. In transformers, you have an attention mechanism where different words attend on the other words. So all of the words are looking at each other and figuring out which words do I depend on for my meaning. The problem with this mechanism is that it's n squared because there's a dense matrix multiplication inside this mechanism, so that if you have a sentence with 100 symbols, tokens or words really, then it's 100 times 100, and if you increase it, then it increases n squared, and that's a problem if you want really large input sequences, and a lot of people in industry are interested in increasing the size of these input sequences that they give into language models. So then they have to have some sort of sparsity in this matrix, so it's not n squared. And there you can get irregular sparsity because random irregular graphs give you a lot of connectivity so that information can flow between words quickly. And then you can squeeze it down so that it becomes linear inside and not linear in size and not n squared. So that's a place where you can get some sparsity. But where you have the highest amounts of sparsity is in graphs and relational data. And graphs really typically come from relational data. Things like who are friends with each other, or what cities are connected to other cities, or things like that. And we have a lot of relational data, and it makes sense that we should want to do some inference or some data analytics on that data. Okay, so then the question is, how should we build? So we already have these graphs. We want to do inference on these graphs. That's clear. There's divisions in most of the big companies doing this stuff. But how should we build them? So there's a couple of possible designs. The common design today is a specialized library for graph neural networks. There's a few variants out there. The two most famous ones are PyGeometric, which is called PIG, or the DGL library, the Deep Graph library. So PyGeometric, I think, comes from Stanford together with some people in Europe, and DGL comes from Amazon. And in these networks, it's really a graph library where you have neighborhood connections, and you compute on it by looking at neighbors of vertices in a graph, and then you take some averaging over that, which is really, that's a matrix vector multiplication, sparse matrix vector multiplication, but they do it with a graph abstraction. The issues with that abstraction, the graph abstraction, which we've seen since Gawa and GraphLab, the problem with that vertex-centric abstraction is that it's very low level. If you want fusion so that you get some temporal locality, you have to hand implement it. If you want to port it to other machines, you have to typically do that by hand, although there are some compilers like Graphit that can do some of that porting for you. But it's a fairly low-level abstraction compared to tensor algebra. So the alternative to implementing graph neural networks in graph frameworks is to implement them in PyTorch. So you can implement them in PyTorch. The problem is that PyTorch only really has solid support for dense arrays. And if you implement graph neural networks with those dense arrays without doing a lot of workarounds to sort of make sparse computations look like dense computations, and then use a lot of gathering and scattering, which is really what these libraries do. Because they're actually built on top of PyTorch, but not in a very abstract way. If you don't do that, and you just implement it directly, then your sparse graph matrices, adjacency matrices, become dense, and it's impossible. There's no way you can scale that. It doesn't scale with the right asymptote. But if you change PyTorch with one change, so you allow, when you declare a tensor, that tensor can be sparse. Then you can implement graph neural networks in PyTorch. You can also implement things like sparse transformer attention mechanisms in PyTorch. So maybe PyTorch is all we need. We just need it to have full support for sparse tensors as well. And what that means is we want to have the constructors of tensors allow you to say that this is a sparse tensor, and then you want no other changes, no other required changes to a library. So if I implement a graph neural network as a dense neural network, I can just then point to a tensor and say that tensor should be sparse. That's the change we need. And that gives us a high-level natural algebra notation. It's the same notation as you find in the papers for the graph neural networks. So clearly it's a natural notation because they use it. And it's makes it easier to compose things together because linear algebra and tensor algebra composes really nicely. And the compilers can fuse computation and reorder and tile and port across the machine automatically, so you don't have to do it by hand. And here's evidence that's a natural notation, because this is the documentation for PyGeometric. And all the documentation for all of their graph neural network layers start with a linear algebra expression. So clearly, that's taken right out of the papers. So even though they're called graph neural networks, they're typically described using linear algebra expressions with adjacency matrices. And then this documentation will always then do this transformation into a graph neighborhood computation in the documentation, and then they implemented that. But better, I think, to just start and end with those linear expressions. Okay, so given that we accept that we should have something like a sparse PyTorch or some design with sparse tensor algebra instead of graph neural networks, then how general should they be? So we could implement kernel libraries where we build something like sparse PyTorch or sparse TensorFlow on top of hand-implemented library routines. And in fact, that's what TensorFlow and PyTorch is currently doing. The problem with that is that you fix the number of you can't implement an infinite number of hand-optimized routines, so you have to reduce everything to a few routines. And you also have to fix the formats. Whereas it'd be a more flexible world if you could do any tensor algebra expression, and you wouldn't be required to reduce your computation to a certain number of tensor algebra expressions. So with the first approach, you can factorize your computation, your tensor algebra expression, into certain hand-optimized routines, then run it on top of a library of handwritten routines. The other approach would be to compile them down all the way to fine-grained code. And that approach would be more general, and that approach would be easier to implement. Okay, so in dense tensor algebra, we do reduce them typically. So there are compilers, obviously, for dense tensor algebra, but a lot of the libraries often reduce computations to gems, partly because they want to execute them on things like TPUs or the Trainium hardware from Amazon. And the way it works is that they take some tensor algebra expression, they reduce it to a sequence of transposes followed by gems. So they make the tensor algebra look like matrix multiplication, hit it with a gem, and then transpose it back into matrices. And that works pretty well. Maybe you take a 2x performance hit, but you don't take an enormous performance hit. And part of that is because the cost of transpose is modest. Okay, but that doesn't work so well for sparse tensor algebra. And the reason for it, there's many reasons for it. One is that transposing requires sorting. So you have to sort your coordinate lists. You need to flatten data structures, meaning with dense tensor algebra, you can just start pretending like a matrix is a tensor or a tensor is a matrix. With sparse tensor algebra, you will need to flatten your coordinates and run over them and move them in memory and compute on them. Unlike dense tensor algebra, compilers are pretty good at producing good sparse tensor algebra operations. But the worst thing is that there's no fusion across operations with this approach. And that can give you asymptotic slowdowns, as we've seen many times. I think many of us have seen this, where if you have something like sample dense matrix multiplication, if you don't fuse it, you get an asymptotic slowdown because you're doing too much work. You're multiplying all the vectors together in that right-hand side matrix multiplication, and then you're sampling from that space, whereas if you sampled and then just multiplied the dot product you needed, you would do less work. So I'm actually out of time. Okay, so I'll go a little bit. Okay, so I have a couple of other examples of why this is a bad idea. On supercomputers, you get the same problem. If you move data, you lose a lot of performance. So this is work by Rohan Yadav, showing that if you generate specialized code for tensor algebra expressions, then you can get much better performance because you're not moving data in memory. If you have to move data to fit to a specialized routine, you lose. Here is 24x on a supercomputer. You see the same if you're trying to implement something much more general, like arbitrary user-defined functions. Here's PyData sparse implementation, where they turn a user-defined function into a bunch of NumPy calls, but they have to move data in memory to do that, so they get a 10x performance degradation by doing that. Here it's 7.5, so it's about an order of magnitude. So you lose this, you get this performance hit every time you try to do this kind of reduction to your library. If you have something sophisticated, you need to do that's far away from the thing you're reducing to that library. So finally, I'll stop here, but the design I think we want a PyTorch or TensorFlow, I don't care. It's one of these dense tensor algebra libraries with sparse tensors and no other changes. Then you want tensor algebra or some general compiler, but you also need other things like user-defined functions, for nonlinear functions, tensor reshaping, so that you can reshape and concatenate your tensors and so forth. You need ways to compose tensors together by putting them next to each other, for instance, and you want masking and various things. And then you want a compiler, you want optimizers, you want a scheduling language that makes that optimizer independent of the specific details of the compiler. You want implementation for CPUs, GPUs, fixed function hardware, sparse spatial data flow hardware, and distributed machines. And you also want a data representation language, which is right here. And I'll end it there. Thanks. Okay, so